Okay, here's a second example for class 24. I think I might have fixed some things that are wrong with it, but let's take a look at it anyway. All right, so we have a projectile. This is a ballistic pendulum problem. It's 0.2 pounds. It's traveling at 1,000 feet per second, and we want to find the angular speed of the system after the impact. So this bullet is going to embed into this 10-pound block that has a 5-pound rod attached to it. Okay, so I cleaned up a little bit of stuff here. This was just a number that happened to be wrong. For the moment of inertia taken about this pin, right? So I guess we're calling this point A, even though I didn't get labeled. And the bullet can be lumped in with the mass moment of inertia because the coefficient of restitution is 0, right? So after the thing, after it does hit and it embeds, that it gets inside here, right? We can include that. It's a very small amount right here. And the bullet doesn't have really much, it's almost like a particle, so it doesn't have its own eye. So we just take the mass of it, and then the distance from here to here squared as it gets included and lumped into that mass moment of inertia. With the coefficient of restitution is 0, therefore the VB is going to be equal to VA, right? Because the bullet's along for the ride. I guess we're deciding to call this whole thing A. That's interesting. And the conservation of angular momentum about that pivot at A is going to have, so the angular momentum before is going to equal to angular momentum afterwards. So here's the 3 diagrams of the system momenta before the bullet hits, the system impulse as the bullet is hitting it, and then the system momenta after the bullet has already embedded, and now it just starts to, the pendulum starts to move. And so we have a velocity, an angular velocity that the thing is going to move at. And one thing that we might note is that the weight right here, it does, if we take the sum of the moments right here, the sum of the angular moments, angular momentum, we would notice that this weight would actually cause a moment, because it does not, that force does not pass through that. But that's going to be a very small weight compared to the impact forces that we would be experiencing, so it can be neglected. So we could simply write that the angular momentum on the left diagram on the system momenta before is really just the mass of the bullet times the velocity of the bullet, right? But that's just momentum. We need angular momentum, so it needs to have a moment arm. So it's going to be this distance right there. And then that's going to equal the system momenta afterwards, which is going to be the total mass moment of inertia about the pin, about A, times the angular velocity. And I guess we decided to use the prime right there to mean instead of 2. I like subscripts 1s and 2s. But anyway, if we take a look at this, we're able to get the omega after the impact. And that's a pretty simple problem. There's really not much more to it. It's almost like too simple. I think the next thing I might ask is what is the energy lost? That's often the question that I might ask. So what we could do, it's not that difficult to find. We would find the kinetic energy before plus the potential energy before equals, not equals, but plus, the energy from 1 to 2, right? If we're going to say that this is state 1 and let's say this is state 2, right, before and after, it's going to equal the kinetic energy after plus the kinetic energy, the potential energy after. All right, and I'm not doing well right here. Okay, anyway. And the potential energy is not going to change, right? After it's moved up, yes, it will change. So the only thing we're going to do is going to find there's going to be a difference in potential energy. And whatever that difference is, that's going to be the energy that got lost, right? That's going to be this guy right here. That's underlining the wrong thing. Kinetic energy in the beginning, kinetic energy after. Whatever is different is going to be this right here. So let's figure out the kinetic energy before is going to be 1/2 mass of the bullet times the velocity of the bullet squared. All right, and then we go plus U12. By the way, that should be it'll end up being a negative number. Just hint, hint. And then we go 1I omega prime squared, and the prime and the square are getting in the way with each other. So let's check it out. 1/2 0.2 32.2, and what do we got? 1,000? Sure. 1,000 squared plus U 1 to 2 is going to be equal to 1/2. Mass moment is going to be 2.239, and the omega is going to be 6.94 squared. I think this is going to be a whole lot. So let's see what these values are right here. And I'm using my pen while the screen is up. That's why we're so completely terrible looking. So we got 1,000 squared. That's going to be a lot. But then 0.2 times it, and 2 divided, and 32.2 divided. All right, so I have what turns out to be 3,106. Right? It's going to be foot-pounds or pounds-feet, whatever you want to call it. Foot-pounds. And then over here afterwards, we have 6.94, that's squared, times 2.239 times, and then 2 divided. And all we're left with is a 53.92 foot-pounds. So this is a very inefficient thing. You can see that U12 is going to be a negative 3,052 foot-pounds. Well, there's a lot of energy getting lost as part of this. And where does it go? Where it goes to sound, it goes to heat. And then maybe it transmits as vibration up to, who knows where it goes, right? And it's probably be even worse than this, because this is almost ideal situation. But if we wanted to figure out what the efficiency was, we would have the energy before, so the energy after divided by the energy for. So it's 53.92 and divided by 3,016. So we're talking about like 0.179%, like 0.2% efficiency right here. That's how lossy this thing is going to be. So anyway, that's an interesting problem. I'll record this one as a separate thing. So there you go. We're done. We discard? Sure.